Welcome to the deep dive. We're moving beyond gym lore and athletic folklore today, diving into a field that's really revolutionizing how we train, recover, and compete. Sports biomechanics.
Hmm.
It's basically the essential shortcut to understanding how the human body resists force and, well, why it sometimes fails.
It's such a critical shift in perspective.
Mm-hmm.
When we analyze elite performance or injury prevention, we stop treating the body just as biology
Mm-hmm.
and start viewing it as an engineering structure,
Mm-hmm.
a kind of high-tech material that's subject to the fundamental rules of physics.
Exactly. And the material you shared with us is fascinating because it forces you to confront this one fact.
Yeah,
Every single sports injury is, at its core, a material science failure.
that's it.
So our mission today is to uncover the foundational physics of how biological tissue breaks down, from simple stress to fatigue, and then look at the cutting edge where, sophisticated computer modeling is starting to replace coaching guesswork.
And to understand performance, you really have to understand failure first. And to do that, we have to start with the load.
The load.
A load is just the total sum of all the forces acting on a tissue or a joint. When a material takes that load, it does two things. It resists internally, and it deforms externally.
Okay, so let's define those two key concepts right away. Stress and strain.
Right.
Stress is the internal resistance the material puts up against that applied force. You can think of it as the intensity of the force trying to, pull or push the tissue apart.
And strain is the consequence of that. That's the resulting deformation, the actual change in the material's shape or its length.
Mm-hmm.
So stress is the internal fight.
And strain is the physical stretch you can actually see.
Precisely. The stretch, the twist, or the compression.
And these forces, they come in different flavors. We mainly deal with three types of stress in sports. First is tension.
Mm-hmm.
That's the lengthening force. It's what your ligaments and tendons experience when they're stretched out.
Then you have compression, which is the shortening force.
Mm-hmm.
Bone is incredible at handling compression.
And the third one is shear. That's a force acting parallel to the surface, which usually happens from twisting or torsional movements.
Now, this is where it gets really interesting because biological materials are just so much more complex than, say, steel or carbon fiber. They have three properties that complicate everything, especially when you're trying to prevent injuries.
The first one being that they're non-homogeneous.
Right. Their properties aren't uniform all the way through. The hard, compact outer shell of a bone, the cortical bone, behaves totally differently than the spongy cancellous bone inside.
So if you treat it all the same in a model, your prediction is going to be wrong.
Completely wrong. And second, they're anisotropic. This is crucial. It means that tissue's strength depends entirely on the direction of the load you apply.
Ah, okay.
So cortical bone, for instance, the sources say it's about twice as strong when force is applied along its long axis compared to when it's applied across it.
It's like cutting wood, isn't it? It's easy to split it along the grain, but it's incredibly difficult to try and cut across the grain.
Perfect analogy. The tissue's internal structure dictates its resistance. So if your training doesn't respect that directionality, you're just introducing unnecessary risk.
And the third property, the biggest challenge.
The biggest one. They're viscoelastic.
Okay.
They have characteristics both a stiff, elastic solid like a rubber band and a viscous fluid like honey. And the big implication here is that their response to stress is always dependent on time and the rate of loading.
So this viscoelasticity, this gives us some pretty amazing everyday examples of why the body's resilience is constantly changing. The first one is called creep.
Right, creep. If you apply a constant load over time, the tissue just continues to deform. It literally keeps stretching out.
And this is the actual physics behind why you're taller in the morning.
It is. Prolonged standing causes the discs in your spine to, creep. That continuous compressive load just squeezes them.
And the source material points out that you can lose up to 17 millimeters of height.
17 millimeters. That's almost 3/4 of an inch.
What?
In just the first 2 hours after you wake up, it's this huge, quantifiable daily change, all because of creep.
That is wild. Okay, so the inverse of that is something called stress relaxation.
Yep. This happens when you apply a constant strain. So you deform the tissue and you hold that length steady. Over time, the internal stress that's needed to maintain that length actually decreases.
So both of these things prove that the body's stiffness and resilience aren't static at all. They're dynamic, they're time-dependent.
Exactly.
So if we compare the key materials, Bone is relatively inelastic, provides huge resistance to compression,
But you have to remember that anisotropy, its strength against tension, is way lower.
which means if a bone bends, it always breaks first on the side that's stretching, the tensile side.
Right, and then you have cartilage, which is the shock absorber. It's remarkably elastic. It can compress by over 50%.
And that increases the contact area inside the joint, which is an engineer's trick for reducing stress concentration.
It spreads the load, exactly. And finally, the tendon. This stuff is enormously stiff, like a compressed spring. That stiffness makes it resilient.
And able to store huge amounts of elastic energy.
And that elastic recoil is critical for powerful, explosive movements. It's why tendon injuries are so performance-limiting.
Okay, so understanding how these materials behave under load lets us formally categorize how things go wrong in sports. We have two major categories of injury.
The first one is the obvious one, traumatic or acute injury. This is a rapid event caused by a single high-magnitude force.
Like a direct tackle causing a ligament tear or a broken bone.
Exactly. But the second one is the stealth killer, overuse or chronic injury. This is the result of repetitive, low-level trauma, microtrauma, at loads that are way below what would cause an acute break.
So it's basically a failure of the body's repair mechanism. It just can't keep up with the continuous damage.
Biomechanically, it's a textbook case of fatigue failure. In
Wow.
material science, if you apply cyclical loading, even at a low force, microscopic cracks start to form and grow over time.
Leading to catastrophic failure eventually.
Right. Things like stress fractures, patellar tendinitis, these are the biological manifestation of mechanical fatigue failure.
And this brings us right back to the predictability of forces. The load you apply actually dictates the failure pattern, which is so crucial for diagnosis and surgery.
It is. If a bone fails because of a bending load, you get a clean transverse fracture, and it starts precisely on that stretching tensile side of the bone.
And what if the load is pure twisting, torsion?
Then you get a spiral fracture. This is the classic signature of a shear load propagating a crack around the bone. You see it a lot in skiing accidents.
Right, when the ski tip catches and the body keeps rotating.
Exactly. Or even in throwing movements, you can get that kind of torque in the humerus.
And then there's that complex combination you often see in collision sports, the butterfly fracture.
Caused by a mix of axial compression and bending. And the amazing thing is, knowing that fracture pattern immediately tells the surgeon and the physical therapist exactly what forces caused the break. It informs the entire recovery plan.
Okay, so let's move beyond the body itself. We have to recognize the massive role of external factors that modify the load we put on our tissues. And the surface we play on is, well, it's paramount.
It really is. We talk about compliance, which is just the inverse of stiffness.
Mm.
A highly compliant surface, like a thick natural grass field, attenuates impact forces beautifully.
It absorbs the energy.
It does.
Mm.
It reduces the shock that travels up your leg. Conversely, low compliant surfaces like asphalt or concrete, they transmit huge impact forces and carry a major injury risk over time.
And this is why standards exist, right? Like the German DI standard for force reduction.
Yeah, which requires athletic tracks to reduce the maximum force by 35 to 50% compared to concrete. They're literally designing out a huge amount of the injury potential from the get-go.
But reducing the impact force is only half the battle. We also have to think about friction or traction. If a surface allows no sliding, think of that sticky artificial turf or rough asphalt, it imposes an extremely high resistance to rotation.
And that's a problem. If your foot is planted and your trank rotates, that rotational force has to be absorbed somewhere.
By your joints and tendons.
And that fixed foot rotation is a major risk factor for non-contact knee ligament tears and ankle sprains. So the surface that was designed to protect you from one force can often expose you to another.
This trade-off is perfectly encapsulated in the running shoe dichotomy. The shoe is trying to do two jobs that are, well, they're mechanically opposed.
They are. Job one is impact attenuation, cushioning.
Yeah.
This is achieved with soft compressible materials, usually EVA foam in the midsole.
And job two, rear foot control, stability. This means limiting that excessive pronation, that inward roll of the foot, which is a known contributor to Achilles issues and shin splints.
The conflict is structural. It's physics. Soft materials cushion well, but they inherently reduce stability and control. They actually promote instability.
So manufacturers are constantly seeking this perfect compromise, but they're fighting the laws of physics.
They are. And this leads to a critical fact you absolutely need to know about your gear. That soft, wonderful EVA foam suffers from something called compression set.
Permanent deformation.
permanent deformation from repetitive stress. Even if the shoe looks totally fine on the outside, a shoe's shock absorbency can drop by about 30%.
30%.
After only 800 kilometers of running, that's just 500 miles.
So that cushioning you bought the shoe for? It's effectively failed long before the tread even looks worn. It's like an invisible expiration date.
That's the perfect way to put it.
All right, now let's move to the really advanced layer. If we want to optimize performance, a jump, a throw, a sprint, we can't just rely on a coach's subjective insight alone. We need computational precision.
And the challenge starts with figuring out the actual internal forces inside the athlete. The first step is something called inverse dynamics.
Okay, what's that?
Biomechanists use external forces that they measure with force plates, and they combine that with high-speed motion capture data to calculate the net forces and moments segment by segment, working backwards from the ground up.
But you immediately run into what the sources call the biggest obstacle in biomechanics.
The indeterminacy problem, yeah.
Which is?
The human body is mechanically redundant. You just have far too many muscles and ligaments acting on any given joint for the equations of motion to produce a single, unique solution.
So if you have 10 muscles crossing a joint, but only 3 equations of motion.
You have a massive information gap. You can't solve it purely with physics.
So what do? Biomechanists have to kind of guess how the body prioritizes movement.
They do. They use inverse optimization algorithms that are designed to minimize or maximize a hypothetical cost function.
A cost function.
Exactly. They'll assume the nervous system is trying to achieve something specific, like, say, minimizing total muscle effort, or maybe minimizing the load on a joint. The algorithm then finds the muscle force distribution that best fits that assumption.
But wait a minute. If the final prediction of how forces are distributed, the one that might lead to a whole new training plan, is heavily influenced or even predetermined by the initial guess about that cost function, how reliable is that outcome?
That is the core challenge.
What if the athlete is actually prioritizing explosiveness, not efficiency?
That's the vulnerability of the method, and you've hit it on the head. The results are an educated prediction, but they're guided by an assumption. Researchers spend a huge amount of time trying to validate that cost function against real-world observations.
So they might start by assuming the body is minimizing energy?
But then they realize that for a maximal sprint, the body is clearly not minimizing energy, it's maximizing power output. And so they have to adjust the cost function accordingly.
That makes a lot of sense. So once we can model those internal forces, the ultimate goal becomes forward optimization.
Right. This involves using simulation to predict the absolute best technique for a maximum outcome.
Like in the javelin throw example.
Exactly. Forward optimization will simulate millions of throws to identify the perfect combination of release parameters: the speed, the angle of attack, the pitch rate. It mathematically finds the theoretically perfect release.
And the visual tools that come out of that, like contour maps, must be invaluable for a coach.
Oh, they're incredible. These maps show you how much the throwing distance changes when you tweak one parameter or another.
And critically, the maps show that if an athlete is already near the optimal solution, tiny variations in their technique don't actually harm performance that much.
But if they are far away from the optimum, even small changes in their technique can lead to these enormous detrimental drops in distance.
So it allows the coach to focus limited training time on the most impactful areas, not just random corrections.
Exactly. It's about precision coaching.
So this deep dive has really shown us that the human body isn't some perfectly elastic machine, but a really complex viscoelastic material. It's subject to both instantaneous trauma and predictable fatigue failure.
And we've seen that performance and injury are controlled by this fascinating interplay between the internal material properties and the external world. The compliance of the running track, the stability of a shoe, even just the rate of load application.
And finally, that modern biomechanics uses these sophisticated computational models to try and overcome the body's mechanical redundancies, attempting to guess the nervous system's priorities to find the best way to move.
So, what does this all leave you with? Well, the models we've discussed can find the theoretically perfect technique for maximizing a jump or a throw. But these models still suffer from a critical limitation. It's known as simulation evaluation.
So we can calculate perfection.
We can calculate it, but we don't yet have the tools to fully confirm if an individual athlete's actual morphology, their muscle physiology, or their strength profile is physically capable of implementing that calculated optimum.
So there's a gap.
A huge gap.
Yeah.
The ultimate challenge isn't just the equation, it's closing the gap between theoretical human perfection and real-world human limitation.